Okay, yes. So we're going to be doing some sheaves today. We're going to be building some sheaves. They're both built mentally in our minds, but also on our computers. So if you've got a computer and want to follow along, we have some links. All the slides are up here at this link, as well as Google Colab Jupyter notebooks, where you can actually see the code in action. So take a scan of that if you're interested. Give you a few moments. And by way of introduction, I'm Michael Robinson, and with Donna Dietz, we're both from American University, and we're going to be teaching some practicality of how to build sheaves and categories. All right. And additionally, these slides are up on Slack as well. So if you're interested, there we go. So we've now heard category theory is a good way to organize models of systems. They may or may not represent conscious systems. In fact, I tend to come from a world where they're probably not conscious, studying things such as engineered systems. All of these magical computers that you have are complex systems that are hard to understand and can be described this way. So the point of the matter is category theory is, in some sense, the theory of mathematical analogies. That's why it's good for modeling. Build a model that is not the real thing. You have the real thing there. You've got some kind of functor that goes between them. That's an analogy. Surprisingly enough, it's actually expressive to encompass and encode all mathematical logic in category theory itself. But in a sense, and we felt a little bit of that yesterday when one of the discussion groups tried to build an actual category. It's kind of too expressive. It's hard to get a handhold. And one of the interesting things is the salient piece that makes the logic work is actually a subset of category theory called sheaf theory. It's a part of category theory, but it provides some useful constraints. My suggestion is you want constraints to provide handholds. Kind of imagine you're rock climbing, you need handholds. You could get to the top if only you could figure out where to grab. Sheaf theory gives you places to grab. So why sheaves? Well, for one thing, and this is almost being a little bit playfully contrarian, sheaves are the universal reductionist paradigm. That doesn't mean that that's the only thing they're good for, but certainly if you want to think in a reductionist way, I have lots of pieces, parts of models, and I want to assemble them into a whole, sheaves are the way to do that. In fact, it's not even so much that sheaves are a way to do that. If you do this in a reasonable way, you will rediscover sheaves. They're unavoidable. The other point is that they really help you moderate between different levels of abstraction. So one thing I think we've been missing in our discussions of category theory is this notion of extent. Near, far, what does that even mean? What does near and far mean when you don't have a notion of distance? You need topology. Sheaves are built on topology, and that makes it work well. So additionally, recently, they're actually practical for doing computation, which is what the software that you can play with is for. All right, so sheaves are universal. So there's a theorem that goes back to the 1960s from Levert, where he proved that formal logic can be rewritten in the language of sheaves. And interestingly enough, you might say, we heard Kurt Gödel mentioned yesterday, formal logic in the classical standard mathematical sense that used in the mathematical tradition with the law of the excluded middle and all those great things versus intuitionist logic, they were at loggerheads. They're both wrong in a sense. Neither one of them is complete. Well, are there other logics? Yes, lots of other logics. Lots of other logics that are somehow more or less expressive. They all can be encoded in sheaves. So Levert proved this in the 1960s. That's cool. Interestingly enough, I'm not aware of anyone who's actually realized this in software in a practical way. Now, on the other hand, you might say, all right, great, what about the other point? Recently, I've proven, this is a theorem that fairly recently, paper that's listed in some of the reading material, is that any framework that purports to be assembling small models into bigger models, that's gonna work in a sense and not do awful things, not give you inconsistencies in some fashion. And there's an axiomatic way to say that. And it's a minimal axiom set. You land exactly on the definition of sheaf. Oh, so sheaves are not only are they universal, they're canonical, they're unavoidable. So any systematic modeling approach that's going to involve little bits and pieces of things put together are going to land you on sheaves. So might as well learn them. So sheaves really help you guide abstraction level. And I think this is important. You know, all models are wrong. Okay, not to be the statistician here. All models are wrong. Some of them are useful. And the question is, how much error are you willing to tolerate where? If you build sheaves of metric spaces, you're actually able to tolerate and measure how much error there is. And then you can answer questions about where is a model valid. As a mathematician, you just assume, hey, the world is exactly the way I thought it is, right? I don't know. That doesn't seem right. As an engineer, on the other hand, I don't think that. I think that all of these models being wrong, I'm going to tolerate some error. Where is the model valid? Sheaves allow you to think about the domain of validity. And really, actually, the same paper where George Box had his famous quote that everyone quotes, he also said it's inappropriate to be concerned about safety for mice when there are tigers abroad. Pay attention to the errors that matter, ignore the ones that don't. So my claim, which hopefully you will kind of see where I'm coming from by the end of today, is that this is a topological notion, and sheaves being geometric and topological and category theoretic give you a way to think about that. So when I say topology, first of all, I do not mean topography. This is topography, the study of maps. The study of topology is, I can't tell the difference between these two things, a coffee cup and a donut, because I can deform one into the other. Both of them have a hole I can grab onto. I can reach my hand through this donut, stick a finger through, similarly through this coffee cup's handle. Now you might say, why would I care about this? Why is this even a reasonable thing to be talking about? Doesn't this seem like dysfunction? Well, the point is, if you have a model that's tolerant to this kind of distortions, it's very, very robust. And this actually shows up in data. So just to make this very concrete and kind of to explain the sort of intellectual person I am, when I heard about topology and was starting to build systems that are topologically sensitive, I said, well, I should be able to see this in some real data, right? So what I did is I grabbed my handy dandy cell phone. I wrote a little program that told me which wireless access points it could hear, collected their signal strengths, and wrote a little vector. Each wireless access point got a dimension, and the signal strength got slotted in. And then I took a walk around the apartment complex where we were living at the time. And I walked around on a little circle. This gives me a high dimensional point cloud. Of course, somehow or another, you guys didn't buy a 52-dimensional projector. But if I project it down to 2 dimensions, you can actually see that there's actually, this point cloud has got a hole in it. There's a loop. Now, this is all very nice. The fact is, this is witnessing the fact that I never went into this region. Now, of course, when I did this, I was very excited, came right back into the apartment and said, hey, look, there's a hole. And my dear wife and colleague said, that's not very convincing because it could be noisy. Why don't you take a different walk? So I did. I changed the topology. I instead walked in a shape of a figure 8 that has a different hole. You notice the circly kind of path has got 1 hole in it. This has got 2. I can grab my hand here and here. And in fact, you can see the data complied and gave me a figure 8 path. So this is valid. Topology is present in our data. If it's there, we should use it. So now when you ask a topologist, a mathematician who studies topology, what should I use for a topology? What should I use for my model? There's actually a lot of options. Each one of these little names on this page is a separate system of axioms to describe a notion of space without distance. There's a lot of them. Some of them are really elaborate. Some of them are rather simplistic. Some of them are rather old and venerable, like manifolds. Some of them are a little more sophisticated, like hypergraphs. What do we need? Well, when you talk to different people, you get different answers. For the purposes of today, and for the purposes of nearly every example that I have worked, it's sufficient to stay down at the bottom of this diagram and study partial orders. We heard partial orders mentioned yesterday. It turns out that they're the right place. And there's a theorem of Birkhoff that guarantees that that's a reasonable place to work. And you build what's called the Alexandrov topology on a partial order. We'll get to what that means formally a little later on in the day. But the point is that this is effectively represented by a directed acyclic graph. You have vertices and you have edges. And while you can have loops that go this way, you can not have loops that go this way. You cannot have cycles. This is good for describing hierarchies. If I have a hierarchy of extents, if I'm down low in the hierarchy versus down high in the hierarchy, that is a well-defined notion, because I can look at my partial order and say, yes, these guys down at the lower level are definitely below these guys. However, within a level, there may be some ambiguity. That's fine. So what is a sheaf? I've mentioned the word a whole bunch of times. We'll see what this is by example. Formally, a sheaf is a kind of functor. It's a functor from the partial order into some kind of data category. And what that means is, from a computational standpoint, is you take your directed acyclic graph. Each vertex gets given a set. Each vertex describes a domain of validity. We'll call that a graph node or a cell. And it corresponds to a model, by which I mean a stalk, or it's got a metric associated with it, some kind of data, some notion of distance. There was some equivocation yesterday about what do the objects in this category represent? Do they represent discrete experiences? Are they very small and atomic, or are they larger? And the equivocation persists. That's okay. Live with it. It's good. When I mean objects in my category, I'm effectively talking about graph nodes. Think of each one of them as a locus of data. It could be an experience. It could be an observation. It could be anything that you want to use to hold some data. Now, then every time I have an edge in my graph, an arrow, a way to go from something that's somewhat more general to something more specific, you need to ascribe to that a function. We'll call that a restriction. And that is, of course, effectively the transformations of the morphisms in the category. We'll call this a sheaf on a partial order. That's the domain of the category, the domain category. And it is of, in this case, we'll work almost exclusively with metric spaces. That's the codomain category. Reason for metric spaces, we can do distance, therefore we can do statistics, therefore we can do all of the kinds of signal processing and such we want to do. It's worth noting the traditional mathematicians, if you crack any book on sheaf theory, you will find that they don't do this. They do sheaf cohomology, and it's kind of inscrutable. Sheaf cohomology studies models in the absence of data. As it turns out, it's provably not noise tolerant, which means while it's great theoretically, it does not perform in practice. And actually, they're kind of computationally burdensome until very recently, and I am waiting, drumming my fingers, waiting for a software release by one of my colleagues to make this more efficient, but not available yet, so I can't share it with you. So the point is, by working with sheaves on a partial order of metric spaces, we handle both models and data separately or together. We can actually prove that they're noise tolerant if you read the papers that are included with the reading material that explains how, and they're computationally more efficient. So learning objectives for today. This is a summer school, yes? So we have learning objectives. Learning objectives today. I want to show you how to build sheaves. I want to show you how to encode them for various problems. They probably won't be the ones you're actually interested in, but then you'll get some facility and some skill in building them, so that then you can build them for your own problems. I want you to derive some actual useful solutions to these problems using the software tools. We've written a library called PySheaf that gives you numerical estimates and allows you to compute things usefully. And with that, we can actually talk about how to measure, localize, and interpret the extent of consistency within a model with respect to observations. In fact, when you think about it a little bit, this feels very much like and very closely aligned with the concept of integrated information. That's not proven yet. Maybe we'll do that next week. Okay, so the way we're going to do this structurally is, just to keep you from getting bored of hearing me speak the whole time, we're going to hand off. And that was our first handoff.